we've got in this textbook because we're going through all of our pictures, all of our different types of quadrilaterals. You should have like lots of patty paper, and only just now am I realizing that you actually needed like a square quadrilateral page, a parallelogram, a rhombus, a rectangle, etc. So, you know, however you want to like copy them down for your notes for the future, or just like, you know, a flip book that you could create. That would be a suggestion now that you can do, because what we just did on page 221 is create a kite. Yeah, like the thing that flies in the sky. The quadrilateral you drew is a kite. A kite is a quadrilateral with two pairs of equal adjacent sides. Adjacent means touching. So if the two sides touch. When the diagonals of a quadrilateral are perpendicular, so that's another vocab word here, and only one bisects the other, so that is another vocab word, it is a kite. And the diagonals of a kite may or may not be congruent. All right, write the name of the quadrilateral on patty paper. Check. Let's go to the next one, trapezoid, one of the last shapes that we need to talk about of quadrilaterals. A trapezoid is a quadrilateral with at least, oh my gosh, too many words, at least one pair of parallel sides. And they like using the at least condition, known as bases. If the other pair of sides are not parallel, then they're known as the legs. So I guess I've got my one pair of parallel sides known as bases. Gonna highlight them yellow. Highlight them yellow. And then if the other pair of sides are not parallel, then they're known as the legs. So legs, highlighting pink. All right. A special type of trapezoid is an isosceles trapezoid. And so isosceles trapezoids, they have congruent legs. Like maybe DZ is the same length as PT. So that's what we're going to do. We're going to use a piece of patty paper to trace the trapezoid, and then we're also going to draw, well, they want you to do use the patty paper to trace the trapezoid. So you have a patty paper of notes for like an upcoming assessment. Genius idea. Draw the diagonals TZ and PD. Straight edge. Draw the diagonals. So TZ, draw that in. Kind of like line it up. Rotate the protractor straight edge just enough to make it count. PD. Check it. Sorry, this takes so long. You can skip ahead in the video, of course. All right, now determine the measures of so check. Determine the measures of TZ and PD. Let's use millimeters for this one. And so you have to also notice sometimes you guys make a judgment call where you don't actually start at 0. You start at a different value. Zoom in. There we go. All right, so we have TZ. Looks like it's approximately, let's see, put the 0 on T and we go by millimeters. So 10 millimeters, 20 millimeters, 30 millimeters, 34, right? 34 millimeters is what TZ is. The measure of TZ is 34 millimeters. I'll show you what I wrote in a second. Let's also measure PD. So again, you got to put the 0, not the corner right here, but you got to put the 0 on P. So you always got to make sure your ruler starts at, you know, a reasonable space to start at. And then line it up. So then we go, every little space is a millimeter. 1 represents 10 millimeters, so, or 1 centimeter. So 10, 20, 30, 31, 32, 33, 34 as well. Turns out both diagonals are going to be the same line length, and because they're the same line length, that lets us know the measure of PD is also 34 millimeters. Do they bisect each other? No. Right? If this is supposed to be the middle up here and call it like E, you can just kind of like see it with your eyes. This line segment, EZ, is longer than this line segment, ET. By the way, I put in E in the middle. We've kind of done that whenever we needed like a middle letter. EZ is not the same as ET. So that means no, they don't bisect each other. The condition is, do they bisect each other both ways? No, they don't. What's the difference between a kite and a rhombus? A kite has adjacent sides that are the same, adjacent sides that are the same, but like they're different, you know, there are at least two different layers, right? The top two sides are different than the bottom two sides, but in a rhombus, all four sides are the same, adjacent, opposite, whatever. What is the reasoning that we can use that prohibits you from using the same process to show base angles of any trapezoid are congruent? Well, let's see, let's measure right here. Measure each interior angle of this quadrilateral. I asked a question, see if we can answer it right now with doing this actual information. So I'm going to extend dt in both directions. I'm going to extend dz in both directions. Oh, this is kind of cool. If you extend the lines long enough, you actually end up creating an isosceles triangle. It's like you actually chopped off this top piece right here. Whoops, get rid of that. So an isosceles trapezoid is like the bottom section of a triangle, an isosceles triangle. Now let's actually measure them. So protractor comes out. And in the protractor, place the circle, the center circle, on the angle itself. Right over the middle of it there. You can kind of see down the camera down into that angle. You got to twist the protractor so that it lines up with T, and then measure. So out this line looks like about 66, right? So if I go 10, 20, 30, 40, 50, 60, each of these little marks is another degree. So it's hitting at about 65, 66 degrees. Angle D is a 66 degree angle. Now do the same thing over here. It should be the same. And it is. So since they're both 66 degrees, now we can measure the other angles. We can measure these up here. And I'll do that, you know, kind of quickly just to kind of prove a point, but it should be 124. No, 114. It should be 114. Think about why I get 114 as I actually go and measure it. 114, 114, 114. And then out here it looks like it's, let's see, 10, 20, 30, 40, 100, 90, 89, 100, 110. It's a little less than 115, probably the 114 that I'm talking about. So what happens if you take these two and add them together? What answer do you get? You know, it's one of those common answers in mathematics for geometry. They should both add up to 180 degrees. The adjacent angles on the base of the trapezoid are congruent. The adjacent. I guess adjacent doesn't mean touching, it just means next to. The adjacent angles. So the angles that are next to each other, like angle D and then angle T, are congruent. You know, that only works because this is an isosceles trapezoid. If one of the lines was tilted a little bit differently, still had parallel bases, but if one of the lines was tilted a little bit differently, then you wouldn't have congruent base angles. They'd all still add up to 180 degrees. It's just they would be different. And still a trapezoid, just not an isosceles trapezoid. Save the quadrilaterals you drew on your pieces of patty paper. You'll need them later. Bet. If anything, you can always come back to these pages, trace the quadrilateral that's actually on this book in those sections, and then bring them to wherever you need them in the future. All right? It might be a good idea to even, like, you know, dog ear these pages just so that you have access to them for the future. Start on page 216 and work your way all the way up to page 222. All right? I'm going to go ahead and do that with this video. The next lesson is activity 3. Thanks for watching this video. Like and subscribe, comment, etc. And I will see you in the next one. Thanks.